Topic 1, use substitution. I chose this topic for review for the AP exam because it is a topic that will be used to solve a lot of integrals, and so if you cannot use substitution, you will be stuck with at a lot of places. So I feel like it's something that will be asked a lot of us on the AP exam. So I like to think about this with do you see du. That's a big hint. I always think about it because I look for the u in the problem and the du in the problem to see if I can cancel things out. So generally, u substitution is used to undo the chain rule while taking an antiderivative. The formula written out of this is the integral of f prime of x times g prime of f of x equals g of f of x plus c. So that just shows that's the inverse of the chain rule. If u equals f of x, then du equals f prime of dx, f prime of x dx, which makes sense. So therefore, g prime of f of x times f prime of f of x dx equals g prime of u du dx times dx, which is equal to g prime of u du. So that's just a lot of messiness to understand that you're undoing the chain rule basically when you're using u substitution. So the most important thing with u substitution is finding u. So how do you find u? Well, the general idea is to look at the function and see if the derivative of one part could be used to cancel out another part of the function. So for example, if you see 2x in the problem and then you also see x squared, you know that the derivative of x squared could cancel out the 2x. So some potential possibilities for where to find u are as follows. It could be raised to the power n, it could be rooted, it could be the denominator, it could be inside of a trig function, and it could be the value that e is raised to, or potentially an a as well. So for my example, I took an example from Module 1, the Lesson 3 notes. Now I chose this because it was one that I had trouble with, and I didn't actually recognize to use the u substitution initially. So I feel like it was a good problem to use for review, because it'll help me review, and it could also help anyone else in the future. So first, rewrite the problem as 2 to the power of x to the power of 1 over 2 times x to the power of 1 over 2. This just helps me visualize more. I like to get rid of the square roots, usually in a problem, dx. So there's no obvious u that sticks out, but we can just take some derivatives and see if anything cancels out the other x part of the function. So just taking a guess, we could try out u equals 2 to the power of x to the 1/2. So if that's the case, first we have to solve for du. So the derivative rule tells us that any function a to the x, the derivative of that would be ln a times a to the x times the derivative of the x in the function a to the x. So therefore, our du equals ln of 2 times 2 to the power of x to the 1/2 times the derivative of that x to the 1/2, which is 1 over 2 to the power of negative 1 over 2 dx. So now if we solve for dx, that gets us to 2 du over ln 2 times 2 to the square root of x times x to the power of negative 1/2. So notice that I left the x to the negative 1/2 in the denominator, whereas it could have been popped up. But if I leave it there, we can now plug it back into the original integral and see if it can be canceled out. So plugging it back into the original integral, we now have the integral of u times x to the power of negative 1/2, which is what I was just talking about, times that dx that we just solved for, which is 2 du over ln 2, 2 to the power of square root of x times x to the negative 1/2. So now we can see where those x to the negative 1/2s cancel out, and we're left with the integral of u times 2 du over ln 2, 2 to the power of square root of x. So now we factor out the constants because our integration rules tell us that we can do that. So it is now 2 over ln 2 times the square root of u over 2 to the power of square root of x. So now we can plug our u back in that we chose to select as our u earlier, and then we see that it is now 2 root x over 2 root x. So those values can divide out just to equal 1. So that leaves us with 2 over ln of 2 times the integral of 1 du. Now that is a problem we can definitely solve. And remember, du is the derivative of 2 to the power of square root of x. So when we integrate the derivative, we arrive at the original value, which is just 2 to the power of x, to the power of square root of x. Leaving us with our final answer of 2 over ln of 2 times 2 to the power of square root of x plus c. Remember, do not forget that plus c. And that's topic 1. Now for topic 2, I chose improper integrals and integration by parts. The reason I chose these is because I felt like Both of these will be topics that will be asked of us on the AP exam, and I didn't want to leave any of them out, so actually we'll end up choosing an example problem that uses both. So it's good to review both for some tips and hints. So improper integrals come in two different forms. So given the integral of a to b of f of x dx, type 1 could be when either a or b or both are negative or positive infinity. So that means the limits of integration are infinity, and therefore it is an improper integral. Type 2 would be when the region defined by the function f of x has an infinite discontinuity on the interval a to b. So we'll see an example of that. So for type 1, we want to replace whatever limit of integration is at infinity with t, and then we'll take the limit of the integral as t approaches infinity or negative infinity, depending on the original limit of integration. So a smaller hint, if both limits of integration are infinite, you want to split the integral into two different limits, one as t approaches negative infinity and the other as t approaches infinity, and that way we can solve that up and add them up at the end. So for type 2, type 2 improper integrals, the first step is to locate where that vertical asymptote appears, or where that the infinite discontinuity appears. So if the upper limit of integration has the discontinuity, which is b, you want to replace b with t and take the limit as t approaches b from the left of the integral of a to t. Notice it's from the left. If the lower limit of the integration has a discontinuity, which is a, replace a with t and take the limit as t approaches a from the right of t to b. Note that it is from the right this time. That is because from the left it would not exist there. It would not be part of the integral that we're actually interested in. So if there are two discontinuities, you want to split the integral of a to b f of x dx into a to c f of x dx plus b to c f of x dx, leaving out that discontinuity in between c. So the second part of this is going to be integration by parts. The general formula for integration by parts is uv minus the integral of v du. And now the most difficult part about integration by parts is recognizing what's u, what's dv. So my question, similar to what I had for u substitution, is do you see du and dv? So integration by parts is used to undo the product rule, similarly to how u substitution is used to undo the chain rule. Picking a u and a dv is the most difficult part, in my opinion. So to find a u that you can either derive until you get to a constant, or derive to a value that can cancel out with the antiderivative of dv. So a lot of times you'll have to maybe take a derivative and see where that goes, and it might not work out, so you just have to start over. So let's look at an example that uses both improper integrals and integration by parts. So this is also from a practice problem that we had, which is the integral from negative infinity to 0 of e to the x times x dx. So right off the bat, we can recognize that this is a type 1 improper integral because negative 1 is the lower limit of integration. Therefore, we will take a limit as t approaches negative infinity, replacing negative infinity with t. So the limit of t approaches negative infinity from t to 0 of x to the power of x times e to the x dx. So now we have to integrate that function. But as you recognize here, quickly it is integration by parts problem as the two functions are being multiplied. So we will choose u equals x because we know the derivative is just 1. So that'll make it very easy. And we also know that we can also choose e to the x as our dv because it is easy to antiderive. So our dv is e to the x, and then the v, therefore, is e to the x. So now if we plug in to our integration by parts equation that I showed earlier, we have x to the e to the x minus the integral of e to the x dx. Now, obviously, the integral of e to the x is just e to the x. Therefore, our answer is x e to the x minus e to the x. So now we have to go back to the limit that we set up earlier. So therefore, we have to take this limit as t approaches negative infinity of the antiderivative that we just solved, evaluated from t to 0. So if we do that, if we plug in t to 0, just our fundamental theorem of calculus tells us that f of 0, the antiderivative of 0, minus the antiderivative of t will equal the integral. That will be solving the integral. So therefore, we have our limit of t as t approaches negative infinity of 0 times e to the 0 minus e to the 0 minus t times e to the t minus e to the t. So we're going to split this up into 3 limits just to make it easier to solve. So first off, we have obviously 0 times anything is going to be 0, so it's just limit as t approaches negative infinity of negative e to the 0 minus, because keep in mind in the original function, in the previous limit, we showed that it was minus t to the et. So it is minus the limit as t approaches negative infinity of t to the et, and then it's plus the limit as t approaches negative infinity of e to the t, because the two minuses, the negatives, cancel out into a plus. So that's just e to the t. So now we split that into the 3 limits to make it easier to solve. And now, obviously, e to the 0 is just 1, and it's negative e to the 0, so the answer is negative 1. Now, minus this limit as t approaches negative infinity, t to the et. We're gonna skip over that for a second here, and just go to the next one, which is the limit as t approaches negative infinity of e to the t. Now, obviously, if t is getting progressively smaller and smaller, closer to negative infinity, the function will just get smaller and smaller, because e to a negative is just 1 over e to that power. So it'll just approach 0 as t approaches negative infinity, so we just call that 0. But now to solve this middle limit, we're going to need to use L'Hopital's rule. So we're going to rearrange this to be limit as t approaches negative infinity of t over e to the negative t, which is just the same as the original function, just put into a different way. So now we can use L'Hopital's rule. So the derivative of t is 1, and the derivative of e to the negative t is negative e to the negative t. And now if we plug that in for as t approaches negative infinity, that will equal 0, because the lower function will just increase as the top stays as 1. So 1 over an extremely large number will approach 0 eventually. So now solving that out, we have negative 1 plus 0 equals negative 1. Therefore, the improper integral converges to negative 1. And that's our final answer.